It's time for Unit 10, Lecture 4, the last lecture of this unit, which will cover fog and precipitation. The last little bit of this water in the atmosphere unit before we eventually head on to start talking about weather and predicting weather and weather patterns. We're going to start with fog. Now, clouds, water vapor that condensed up in the atmosphere, usually above 2,000 meters or so, right? Above quite a few feet. However, fog is water vapor that has condensed very near the Earth's surface. And the whole reason for this is that the air close to the ground has cooled. The big difference between fog and clouds, fog is near the surface of the Earth. Clouds are up in the air. However, fog and clouds form in slightly different ways, so there's also a difference because of how the fog forms. But the big thing to remember is fog is close to the surface, and clouds are up in the air. So that's the main distinction between a fog and a cloud. So one type of fog is radiation fog. And this comes from the nightly cooling of Earth's surface. Now, you know, the sun heats up the Earth during the day, and during the night, the air starts to get thin, gets to get colder and colder because the surface re-radiates some of that energy, but it doesn't give off as much heat as it does during the day when the sun is heating it. So, if the air on contact with the ground gets chilled below the dew point, remember the dew point is the point where water condenses, the water vapor will condense into droplets, or fog. This is called radiation fog. Alright, the whole reason it's called radiation fog is because it results from the loss of heat by radiation. So there's no more heat from the sun at night because the sun is not hitting the surface and heating the surface of the Earth anymore. So we got what is called radiation fog. Second type of fog is advection fog. Alright, we've already talked a little bit about advection 2 lectures ago, at the end of lecture 2. Alright, and this is when warm, moist air moves across a cold surface. So it's either warm, moist air moves over from land, moves over a cold body of water, or warm, moist air from water moves over a cold body of land, and either can happen. It's very common along coastlines, and this happens where warm, moist air from above the water moves over a colder land surface, usually in the mornings or at night. In the middle of the night, the water of the ocean or the Gulf of Mexico retains more heat, so the air over the Gulf or the air over the water there is warmer. That warm air moves over the land, which doesn't hold heat as well as water, so the land is colder, and that air gets cool below its dew point, and you get a fog. So that's our second type of fog, is advection fog. The third type of fog is upslope fog, and it's named really well. It's named based on what is happening. Alright, it's from the lifting and cooling of air as it rises along a slope of land. So there's also lifting that can produce clouds as the air moves up over a mountain. Well, this is if those clouds form, or if that condensation happens right at the land surface, we've got what is called upslope fog. And finally, we have steam fog, which is a little layer of fog that forms as cool air moves over a warm body of water, like a river. And that's the fourth type of fog. Once again, here is that advection fog. We got here, in this case, we have warm air over land moving over water. Alright, like we can see in this picture here. Alright, here's the land. And all that water around is covered in a fog. And that's because the warm air moved over the cold surface of the water. Right. Conversely, like we could have warm air in the water over the water moving over the land and causing the fog there. Upslope fog, we got the air moving toward the slope. It starts going up the slope, and the fog forms on the slope as it reaches the dew point or that condensation temperature. Alright, and so it forms on an upslope. Here you can see a picture of that. Here's the base. There's up the slope of the mountain. You see this fog forming along the slopes. Alright, that brings us away from the clouds and the fog to precipitation, which we're familiar with around here, especially snow these last few days. Alright, there are 4 major types of precipitation. You know them all, you've seen them all. We're in one of the lucky places where all 4 happen. Alright, there's rain, which is liquid precipitation. PPT is a short form or an abbreviation of precipitation. There's P, P, T. Alright, precipitation. Yeah, there's another T in there. I could have picked a couple of T's, but PPT is precipitation. So rain that is between 0.5 millimeter and 5 millimeters in diameter is called a raindrop. Alright, if it is less than 0.5 millimeter, we call that drizzle. That is a very, very low precipitation amount of drizzle. Alright, these aren't necessarily values that you can see with your unaided eye, especially like 0.5 millimeter. Judging 0.5 millimeter from a millimeter in diameter of a raindrop is tough. You can kind of feel it though. You can feel the size of raindrops. You've felt heavier raindrops and lighter raindrops, but that's the big thing. Second type of precipitation is snow, and snow is the most common form of solid precipitation. Rain's the most common form of precipitation all the way around, but the most common form of solid precipitation is snow. It has a vast number of different shapes and sizes. No snowflake is exactly the same. You've all heard that before. Snowflakes are bigger the closer they are to freezing. So you get the biggest snowflakes, like if over this weekend we had pretty big snowflakes, and that is because the temperature was pretty close to 32 Fahrenheit, which is freezing. So the closer you are to freezing, the bigger the snowflakes are, and the size decreases as temperature decreases. Third type of precipitation is sleet. Sleet, also called freezing rain. Alright, so the rain falls through freezing air and forms sleet. So it starts off as liquid from the cloud, comes down, freezes as it's coming down, and it lands as ice. Or hits as like an icy, watery mixture. And finally is hail, and hail are actual chunks of ice, and they form in the cumulonimbus clouds. It's very rare to get hail without having a cumulonimbus cloud, and we'll see the cycle that has to happen, and it's a convection cycle. And as the hail balls go through this convection cycle, they get larger and larger and larger, and we'll see that in a diagram in a minute. Those are the 4 types of precipitation: rain, snow, sleet, and hail. Here, and you have this picture in your notes, here is that picture I was talking about. We got a big old cumulonimbus cloud here. You know, it's starting from below 20,000 feet up in the air, and the cloud itself reaches all the way up to 50,000 feet. And what happens to make these clouds is you got the air coming in, and then it's rising rapidly. And as it rises rapidly, it cools. We got the freezing line right there. And as it cools, a couple things happen. So we end up number 1 right here, where anywhere you see number 1, this is a rain-free region. It's produced by updraft, and and that is that air getting pulled up into the cloud. That is the updraft. All right, and it suspends rain up in the air and keeps hail aloft because it's like almost like a wind blowing up. All right, you don't really see it much. All right, and this also produces a strong radar echo. So if we're using radar to track a storm, the strong storms that come through in red mean there's a lot of updraft. And if you have enough updraft, what ends up happening is the cloud starts forming and touching the ground, and you get a tornado. Anyway, the hail nucleus, the ball of hail, gets uplifted by that updraft. All right, and it is carried and continues to grow inside as it collides with other pieces of hail and cold raindrops. Number 2, right here, some of that hail gets too heavy or gets blown out of the updraft and begins to fall to the earth, and you get a little hailstorm right here where you see number 2. Number 3, if the updraft is strong enough, as that hail begins to fall to the earth, it gets caught in the updraft again and goes through the cycle again and starts hitting more hail balls and gets growing and growing. All right, and this process can happen several times, where you go from 1, and then it starts to fall, and then it gets caught again to 3, back to 1, to 2, to 3, and it just circles around and around, and the hail ball the chunk of ice gets larger and larger and larger. Eventually, the hail gets so heavy that the updraft can't keep it up in the air anymore, and it falls to earth. The stronger the updraft, the larger the hailstones. And the hailstones can cause significant damage. There have been reports of hailstones the size of dimes or even the size of golf balls, and they could dent cars, break windows, and seriously hurt people. Well, precipitation itself, what exactly causes it? 2 things. One is called coalescence, the other is called supercooling. Alright? Supercooling sounds exactly like what it is, and we'll talk about that in a little bit. Coalescence might be a new word to you. And coalescence has to do with gravity. And it's gravity that causes the drops to fall. Alright? And you've all seen coalescence before. Coalescence is like what happens if you're driving in a car during a rainstorm and you start watching the drops of water on the windows as they start heading down those windows. I used to love watching that as a kid. I still like watching it sometimes, but typically now I'm driving, and so watching a raindrop go down my windshield is not as safe as, watching the cars around me. Anyway, gravity causes drops to fall. As they fall, the smaller drops combine to form larger drops. And this combining process is coalescence. So it's the small drops combining to form the large drops as they hit each other. And just like as you see raindrops going down a windshield or the window of a car, as a couple of the small ones combined, it forms a bigger drop, which is heavier, and then it usually eventually zooms down the window pretty fast. And so I used to play little games, and yeah, I was an only child, so I was a lonely kid, but especially on car trips. But I'd watch it, and I'd try to see I'd pick 2 raindrops, and I'd watch them and see which one would get to the bottom the first. And it was usually whichever one coalesced, although I didn't know that word at the time, which one joined up with the most other raindrops to zoom down the window. And sometimes they would join together, and I called that a tie. And I would just keep watching and watching and see how good I was at guessing who would win. and everything. Yeah, I know. That's the... Wow. Okay. Second thing that causes precipitation is supercooling. And that is where a substance is cooled below the freezing point, or the condensation point, or sublimation. It's cooled below the point when a phase change would happen without going through a change of state. So it gets cooled below freezing, or cooled below condensation. Alright, and this can happen based on air pressure. Sometimes it can happen based on different things being dissolved in the water. And so anyway, when something super cools, it might not go through the phase change until something disrupts the molecules, and all of a sudden, in a snap, they will switch state. So the whole thing about supercooled water droplets don't freeze because there are no freezing nuclei, or not enough freezing nuclei, and that is something for the ice to form on. Very similar to condensation nuclei. After you have the condensation nuclei, which makes the water droplets, then those water droplets need a freezing nuclei to freeze onto. And so they are solid particles suspended in the air. And they have structures similar to the crystal structure of ice to kind of get water aligned into the right shape. And if there's not enough of these, the water gets colder and colder and colder until something comes that the water can freeze onto. And that something could be like the wing of a jet or something. That's a lot of times how ice starts to form on the wings of jets. And why they use a de-icer to try to have something to disrupt these freezing nuclei. So as the water gets super cooled, alright, ice crystals eventually form on the freezing nuclei, and as they increase in size, they eventually get enough mass to no longer stay up in the clouds, and they fall as snow. If the ice crystals melt and turn into rain as they go through the air, then we get really big raindrops. Alright, and we see these in summer thunderstorms. So sometimes really big raindrops are actually coming from super cooled water up in the clouds. Even though it might be 70 degrees, 80 degrees on the surface, up in the air, in the clouds, it could be around freezing. You know, if you're talking about 40, 50,000 feet up in the air. And so they start coming down as a solid, either as a chunk of ice or a big snowflake or something, and then as they move through the warm air, it melts and you get a big raindrop and it smacks you on the forehead. Or you catch it on your tongue and you're like, water. Alright, and this is just like kind of showing you a cumulonimbus cloud. These arrows up are the updrafts. They go up. They go above the freezing level and start to super cool. Little black dots would be freezing nuclei or solid particles of water or snow coming down. And then as they start to fall, they start coming down. This creates the electrical charge that can build up. There's a lot of static electricity built up in here. That's released as lightning. But anyway, you got the water vapor moves up, and then it super cools to way below freezing, and if it touches one of these freezing nuclei, it could join onto it, and you get a big snowflake, which eventually falls to the earth, and then if it's warm enough, it turns into a big raindrop. A big tool that we use to track these kinds of storms, especially with the cumulonimbus clouds, but really all types of clouds and storms, is something called Doppler radar, and you've seen this. This is the green and yellow and red pictures that you see on a TV weather forecast, or you can even look up radar maps. Alright, and the whole idea of this is sending out a radio wave to bounce off the rain or snow. So we send a radio wave out. Alright, so here's our radar tower. Alright, this is a radar tower. And it sends a radio wave out till it hits a snowflake. Alright, and then that bounces back. And so it will hit the snowflakes, bounce back, and depending on how long the wave takes to return, we can figure out how far away the rain or the snow is. We can also determine the location, the direction of movement of the precipitation, and even the intensity. The more waves that are bounced back, the more rain there is, so the stronger the storm is. And the bigger the particles. And so when we can see all that, we can start to predict where the weather's going. We can figure out where that storm is headed. We can find the direction, we can find the speed, the location, and how strong it is, and let people know, hey, there's a storm coming your way. That's really been a useful device in the last 50 years or so to really communicate weather forecasting. We can forecast storms and kind of watch the radar to see our storms coming our way. And we'll talk about Doppler radar and predicting weather a little bit more in the next unit, as we look for more long-term projections. I mean, Doppler radar is something that we can watch. We can watch the radars from around Rochester and Buffalo and get an idea of what's coming our way in the next day or so. But we can do extended forecasts by knowing some basics about weather and what's happening with the air and everything beforehand, and even know, okay, we see something here, this is probably going to produce some kind of precipitation. And then as it gets closer, both in time and in distance, we can start using the Doppler radar to get a better picture of what is happening. And that is it for Unit 10 and for this video lecture. So if you have any questions, please bring them in and ask. And you guys have a good night.